We generally credit the creation of the periodic table solely to Dmitri Mendeleev. The reality is that Mendeleev wasn't in it by himself. There were many other scientists who had identified trends and patterns amongst the known elements at the time. Mendeleev was just the one who basically took that. He's the first one to take that and put it together into a structured format, what we now know as the modern periodic table. The periodic table is basically an organization of all those trends and behaviors and patterns that scientists had recognized over the years. Now, early periodic tables organized the elements increasing by mass, even though there were a few inconsistencies with that. In the early 1900s, with the discovery of the proton, there was a scientist, Henry Moseley, basically modified the periodic table and modified what we know as the periodic law based on this new information. And the periodic law is the idea that the properties of the elements are a periodic function of their atomic numbers. So what this means is that when you organize the periodic table by increasing atomic number, that we will get a repeating pattern of these properties where we see trends. We see trends both as we go down the groups on the periodic table and also as we go across the periods or the rows. Now, there are a lot of factors that affect the properties of atoms, but for a lot of the trends that we look at, there are two major factors that we want to look at. These two major factors are energy levels and effective nuclear charge. So energy levels is something most people are usually pretty familiar with. It's basically the number of shells in the Bohr model. So when you draw Bohr models, you have all those concentric circles. However many of those energy levels you have, that's what we're talking about here, how many of those circles we have. On the periodic table, these are represented by rows. So the first row is the first energy level, the second row is the second energy level, the third row is the third energy level, et cetera, et cetera. The other one is effective nuclear charge. Effective nuclear charge, this one, basically, there's a few different ways that you can calculate this. We're actually just going to take the simplest approach, which isn't 100% accurate, but it works for the vast majority of what we're looking to do. So what we do with effective nuclear charge is we take the number of protons that are in the atom, and then we subtract from that the number of shielding electrons. And a shielding electron is any electron that's between the nucleus and the electrons we're looking at. Most of the time we're looking at valence electrons, so usually it's protons minus the non-valence electrons, or what are referred to as core electrons. But you can technically look at any particular electron that you want in there. What effective nuclear charge is, it's basically the charge of the nucleus that the electron experiences. The shielding electrons reduce how strong the pull is from the nucleus on the electrons beyond them. So when we look at effective nuclear charge, we're basically just looking to see how strongly is the nucleus influencing that particular electron when we consider the electrons between the nucleus and that electron. Let's actually try doing that with a magnesium atom. So we'll look at the effective nuclear charge for the magnesium atom. To the right here, you have a Bohr model of the magnesium atom. And when you look at it, you'll notice that there are two valence electrons, right? These are our two valence electrons. Between the nucleus and those two valence electrons, there are another 10 electrons, right? We have 2 on the first energy level, we have 8 on the second energy level, so that's a total of 10 shielding electrons. The nucleus has 12 protons. So in order to calculate effective nuclear charge, we would say that the effective nuclear charge is the 12 protons minus those 10 shielding electrons equals 2. And so we say that the effective nuclear charge on those valence electrons is a positive 2 charge. That means that those 2 electrons on the outermost energy level, those valence electrons, are really only experiencing a pull from the nucleus as if the nucleus only had 2 protons. Okay, they don't experience the full positive 12 charge from those 12 protons. They only experience a plus 2 charge from that nucleus due to all those shielding electrons. So now that we've talked about those two major contributing factors, let's talk about some of the periodic trends themselves. There's actually a lot of different periodic trends, things like melting point, density, these sort of things are also characteristic of these trends. The three ones, though, that we're going to talk about specifically right now, these are atomic radius, ionization energy, and electronegativity. Now, the way that we define atomic radius is that it is half the distance between the nuclei of two atoms of the same element that are covalently bonded. Now, this seems kind of an unusual way to describe this. You can think of atomic radius just as the distance from the nucleus to the outermost electrons. The reality is that finding where the outermost electrons are is really tough, because if you remember, electrons are probability based. We can't identify exactly where they're located. So but we can find the nuclei of atoms. So if we bond two nuclei together, create a diatomic molecule, then we can measure where the nuclei are and say that, okay, well, half the distance between that is the radius. So that's usually how we define it. But like I said, if you think about it just as the distance from the nucleus to the outermost electrons, that works fine. Ionization energy. This is the energy required to remove an electron from an atom in the gaseous state. Basically, how much energy does it take to take an electron away from an atom? We say gaseous state just because when atoms are in their gaseous state, they're not interacting with other atoms, so it just simplifies the process. For our purposes, we're going to be talking primarily right now about first ionization energy. And first ionization energy is referring to the electron that requires the least amount of energy to remove. So usually one of your valence electrons is going to be one of those electrons that we get rid of. But ionization energy in general can refer to any electron that's in the atom and how much energy it'll take to get that electron away from the rest of the atom. The last one we're going to talk about for right now is electronegativity. Electronegativity is the tendency of an atom to attract electrons in a chemical bond. This deals with, once atoms are bonded together, how strongly does one atom pull electrons versus the other. You already know this concept in terms of covalent bonding and ionic bonding, where covalent bonds tend to share electrons very equally because they have equal pulls on them, and ionic bonds tend to shift the electrons more towards one side than the other because one atom pulls significantly stronger on the electrons than the other one does. So let's start by talking about atomic radius. We'll start with the easier trend. The easier trend to look at is usually going to be the trend as we go down the groups. So as you go from the top of the table to the bottom of the table in any group on the periodic table. And when it comes to going down the groups, this tends to be the easier one to think about because, remember, as we go down the group, we're increasing the number of energy levels. That's our big factor, the change in number of energy levels. So hydrogen has one energy level. If we just look at the first group, hydrogen has one energy level, lithium has two, sodium has three, potassium has four, etc. When it comes to atomic radius, that makes it really easy to think about because as we add more energy levels, we'll see an increase in the size of the atomic radius. Now, when we look at the trend going across the table from left to right, okay, in this case, because this is where we're going to look at effective nuclear charge. And as we go across the table, our effective nuclear charge is actually going to get larger as we go. When you start at hydrogen, you have an effective nuclear charge of +1. And this will apply to all neutral elements in the first column. And then as you go across the table, each group is going to increase in effective nuclear charge across the representative elements. Going from that +1 in the first column all the way to +8 in the last column. Because of this, as you go from left to right across the periodic table, the valence electrons of the atom are experiencing a stronger and stronger pull from the nucleus because of this greater effective nuclear charge. This is going to result in those valence electrons being pulled in tighter and tighter, closer and closer to the nucleus as you go across that the same column. So going like lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine to neon, we're going to see a steady decrease in that atomic radius. So because we have this increase in atomic radius as we go from the top to the bottom of the table, and as we go from left to right, we see a decrease in atomic radius. That means that our largest atoms are going to be down here in the lower left corner, whereas our smallest atoms are generally going to be up here in the upper right corner. That means as we go from the upper right to the lower left, we're generally going to see an increase in atomic radius. There are exceptions through the periodic table. However, for the most part, this is the general trend that you're going to see when it comes to atomic radius. So now let's talk about first ionization energy. Again, when it comes to first ionization energy, we're going to be removing the electron that requires the least amount of energy to remove from the atom. This is generally going to be your valence electrons. So we're going to end up removing one of our valence electrons when we do this. And when you're talking about quantum model, generally this is also going to be, if it's on the same energy level, like a 2p electron rather than a 2s electron, since 2p electrons would be easier to remove than a 2s electron. And we're going to look at the same kind of trend. So we'll start again by going down the groups. So when we look from the top to the bottom, so again, hydrogen, lithium, sodium, potassium, rubidium, on any particular group, we go from the top to the bottom. Your atom is getting, again, larger as we go down. That means that these electrons are getting further and further and further away from the nucleus. Well, the further electrons get from the nucleus, the harder it is for the nucleus to hold on to it. You may remember from Coulomb's law in physics classes that the further two charged particles get away from each other, the weaker the interaction between them gets. So as we go down this group, because of this increase in size, the pull gets weaker and weaker and weaker, and that means that we're going to see a decrease in our first ionization energy. So this is an opposite trend to the atomic radius, which again makes sense because the bigger the atom gets, the weaker the pull from the nucleus is going to be on those valence electrons. So now if we look at the trend as we go from left to right across the table, so going again like lithium, beryllium, boron, carbon, etc. Now we have an increase in effective nuclear charge. And increasing effective nuclear charge means that those electrons are feeling a stronger and stronger pull from the nucleus. Well, the greater one of the charges gets, so you've got this one electron that's being pulled in by the nucleus, and the nucleus charge, that effective nuclear charge, is increasing as we go across. This is going to lead to a stronger pull on those electrons. That means it's going to be harder to rip that electron away from the atom. And therefore, what we're going to see is an increase in that first ionization energy. So again, if we look at the overall trend on the table, because we're decreasing as we go down groups and we're increasing as we go left to right across the period, in general, we're going to find our lowest ionization energies down here in the lower left corner and our highest first ionization energies in the upper right corner. That means that as we go from the lower left to the upper right, we're generally going to see an increase in first ionization energy for the atoms. Again, this trend is completely the opposite of atomic radius. And just like with the atomic radius, there's going to be some times where it doesn't completely line up with that. And at a later point, we'll talk about some of the inconsistencies you run into with first ionization energy. So the last one to talk about here is electronegativity. Electronegativity, again, this ability of the nucleus to attract electrons. Well, this is going to work very similar to how ionization energy worked, because when you have electrons that are less strongly attracted by the nucleus, it's easier to remove them. So again, if we look at the trend as we go down groups, so going down hydrogen, lithium, sodium, potassium, etc., we're going to see that as that atomic radius gets larger and larger and larger, that the ability of the nucleus to pull in those bonding electrons, which again are going to be valence electrons, those bonding electrons are not as attracted to the nucleus, meaning the nucleus doesn't pull them in as strongly, and this reduces the electronegativity. This is exactly what we saw with the first ionization energy. And similarly, just like with the first ionization energy, when we go from left to right across the table, we're going to see that same kind of trend. The increase in the effective nuclear charge means that the nucleus more strongly pulls those valence electrons. So those bonded electrons get pulled more strongly in these cases. And therefore, as we go from left to right across the table, we're going to see an increase in those electronegativity values. Just summing this up again, if we look at the table, because we're decreasing as we go down and we're increasing as we go left to right, just like with the first ionization energy, we're going to find our lowest electronegativity elements are down in the lower left corner, and our highest electronegativity elements are in the upper right corner. And so as we go from the lower left to the upper right, we're going to see a general increase in electronegativity. And once again, there's going to be inconsistencies, but as a general trend, this will apply.